All right, guys, so here is our third video of review. I'm going to kind of go fast with this one because really this should hopefully be just review, but you never know. All right, so really quickly, we're going to touch all of these topics, and I want to start specifically with the most general, which is going to be just looking at the periodic table and understanding it in its entirety. Before we left, we should have written down all of the charges on the periodic table. Okay, and those are your oxidation numbers. And the reason for these is, remember, these elements will lose an electron to become a noble gas. Okay, and when I say to become a noble gas, remember, it's just to get the configuration that looks like a noble gas, meaning that they are stable. Every element on the periodic table wants to be stable. The most stable are the noble gases, and everybody wants to be like a noble gas. Have an octet rule. There is, of course, one exception to that octet rule, and it's hydrogen and helium. Of course, hydrogen just wants one more electron, and helium doesn't want any more, but it has 2 electrons, and it does not have 8, it only has 2. Okay, so make a long story short, think of a game board. All of these guys act the same because they all want to lose an electron. All of these want to gain an electron. Gain an electron, you look like neon. Lose an electron for sodium, you look like neon. It's all about getting that noble gas configuration. All right, now, with that being said, please remember hydrogen is a nonmetal. That's why it's colored the way that it's colored. Okay, it does not have similar properties as everybody else in the family that it's on top of. It was just one of the places that they started to put hydrogen, and it made sense based on other properties. Okay, with that being said, you have this imaginary line that separates the periodic table into basically 2 distinct pieces. If I put something there just to show you, okay, majority of your periodic table, with the exception of hydrogen, are metals. 90% roughly of the periodic table are metals. The other 10% or so are nonmetals and metalloids. Okay, so you have your nonmetals. Yes, these are halogens, but they're also nonmetals. Yes, these are noble gases. They're also nonmetals. Okay, so all of these guys are nonmetals, including hydrogen. Then you've got your stair step, and whoever basically goes along the stair step is a metalloid, having properties of both metals and nonmetals. That's why they are where they are. Okay, depending on who you ask, polonium counts as a metalloid, and so does actinium. Acetine. Apologize. It's up to you and who you talk to. In my opinion, I don't normally count them as metalloids, but in this case it does. And I think on your web quest that you did, I think that it just stopped there. So yes, you can go from groups 13 to 17 in a periodic table of metalloids, but since you guys did your web quest, and your web quest specifically only said 13 to 16, really your metalloids only go 13 to 16, just like this one is showing. All right, so also, so that I can verify and make sure that you guys understand things. Yes, carbon is a non-metal. Carbon is a non-metal. Some of its allotropes, which are like diamonds or graphite or charcoal, some of those things can actually have metallic properties, specifically conductivity. So if it shows conductivity, then clearly it's going to be a metalloid. All right, and it's only because it's so close that it may actually have those properties. But it has to tell you or give you that property. If it doesn't say that it's conductive, then clearly it's a nonmetal because it won't do anything else. Same thing with tin. Some of you said that tin was a metalloid. No, tin is a metal. Okay, yes, it's close to the metalloids, but tin will have all the properties of a metal unless otherwise stated. Okay, so make sure you read the properties. The properties will tell you, and you need to know that metals are malleable, they're ductile, they conduct electricity, they react in acids, all that kind of stuff. And obviously the nonmetals do all the opposites. Okay, they don't react with acid, they're not conductive, they're not malleable, and which means brittle. Okay, things like that. And lustrous. Metals are lustrous, they shine. All right. And then, of course, the guys in the middle will have properties of both, like you guys told me. You could have a shiny, brittle object, which is silicon. Silicon's beautiful. It's shiny, but you can hit it with a hammer and it breaks into thousands of pieces. Okay, it almost gets into dust. All right, so there's your basics of charges and metals and nonmetals and metalloids. Okay, your s, p, d, and f orbitals. Okay, that's the next thing. If I show you on the periodic table, okay, something that looks like this. If you notice, it breaks up into 4 sections. There's your s's, there's your p's, your d's, and your f's. Okay, the s for helium goes over here just so it makes it look nice and neat. Okay, s's have a maximum of 2 electrons. That's why there's 2. P's have a maximum of 6, and if you count across, there's 6. D's are 10, there's 10 there, and F's are 14. All adds up. Okay, so when you're talking about the blocks on the periodic table, when you're doing your electron configurations, 1s2, 2s2, 2p6, so on and so on. And then when you get to the 4s, like I kept telling you guys, remember that get to that 4s. After 4s comes 3d. So these guys are always 1 less than the row number. And then these guys, when they come in, are always 2 less than the row number. See, 6s and then 4f. So that's really just super basic about the periodic table. Okay, now if we go back to talking about the colored periodic table, okay, you have your orbitals done. Now we're going to go to Bohr models and valence electrons. Super duper important. The families are the way they are and their properties are the way they are because of valence electrons. Okay, so all of these guys in group 1 have 1 valence electron. Everybody in group 2 has 2. All the way over to boron. These guys have varying, that's why they're called transitional metals. They transition from one to another. Group 13 has 3, group 14, 4, and so on and so forth. Again, valence electrons over here have 8 with the exception of helium. It only has 2 electrons, so its outermost electrons are 2. Okay, so review. Here we go. All of these guys lose an electron to become stable. That means they have 1 valence electron. Notice they're in their s's. These are in our p's. S orbitals, p orbitals are the only valence electrons you are going to have. So when you're doing electron configurations or something asks you about electrons that are in their outermost shell, it's only s's and p's because those are the only ones where you're going to have your charges. Those are the only ones that are picked off because they're in their outermost shell. So for example, if I did a Bohr model for, let's do nitrogen. Okay, so here's nitrogen. Nitrogen's number 7. 7 electrons, right? Okay, so really quickly, I'm going to draw nitrogen. I'm just going to do it in the very center just to be really fast. Okay, we all know that there are 2 electrons in the first shell. 1, 2. Now you move on. Second shell then means that you're going to have 5 more. 7 minus 2 is 5. So 1, 2, 3, 4, 5. Okay, so which ones are your valence electrons? That's going to be the 5 in the out. All right, now guess what? There's your 1s, and then 2 of these are your 2s's, and then the other 3 are your 2p's. Sorry. So 1s2, 2s2, 2p3. And if you count that up, that clearly adds up to 7. 2 plus 2 plus 3 is 7. 7 electrons, so we're good. Well, your valence electrons are your last s and p orbitals, which are right there. Which means, just like when you drew this, when you do your Bohr model for nitrogen, 1, 2, 3, 4, 5. It's the 5 in the out. There's your 5, and 2 plus 3 is 5. So there's your outer electrons. This is your Lewis dot. Okay, so your Bohr model gives you your Lewis dot structure. But again, you don't even have to draw this to get this. If you know your electron configuration, look for your last S and your last P. So with that being said, let's do another one, and let's not draw the Bohr model. So let's do something like, let's do calcium. No, let's do something harder. Let's do strontium. It's not really much harder, but you know what I mean. Okay, strontium is number 38 on the periodic table. Okay, we didn't really do a lot of things with this. It's just a little further on the periodic table. I told you guys really to memorize the first 20. So when I look at this one, it's really far down on the periodic table. Well, it's in the second column. Because strontium is in the second column, that tells me it should have 2 valence electrons. So all I really have to do is put 2 dots on it, and I'm done. There's my Lewis dot. Okay, 38. I don't care about all 38 electrons. All I care about are 2 of them. So if I do my electron configuration for this, bear with me, I'm just going to go really fast. And I write this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s. Notice strontium, 5th period, 1, 2. Second one in, 5s2. I told you guys that it's the last S and P electrons that are your valence electrons. Well, last S and P, not P and S, S and P. So notice my last S and P, or just S, is 2. So I have 2 valence electrons. There they are.